perhaps I could say a few words while we wait for the late stragglers.
Okay.
I just wanted, on behalf of YorRobots, to welcome everybody, to thank you all for attending. This is the first YorRobots seminar of this academic year. If you perhaps have heard about YorRobots, but in case you haven't, YorRobots is a network of academics, researchers at all levels at the University of York working in the area of robotics. In spite of all the situation with which we remain very active. And I'd like to thank Anna for contributing to the restart of our series. We had to cancel the speaker, but it's very, very, very nice that he was able to join us as a very, very senior speaker. I'm looking very much forward to this talk today. YorRobots involves or is represented by researchers in 11 departments. Robotics at the University of York is a very multidisciplinary activity. I'd like you to all think about joining, if you haven't yet, the email list of YorRobots, RAS-group. You can subscribe and we will find out about the very many lovely seminars, events, funding opportunities that we promote. So welcome, and Anna, Themis, thank you very much.
Thanks, Anna. So, and thanks to you, Themis, for agreeing to join us. It seems like a very long time ago since we discussed Themis coming to York in person. And now, obviously, a lot has happened between then and now. So we are really glad that you can join us, Themis. Thank you. If it's all right with you, then I'll introduce you a bit more thoroughly, and then we can launch straight in. But something that I've learned from my colleagues is that it's usually better to know in advance how we should hold on to questions. But I think it would be good for our audience, if you have some questions, jot them down and hang on until the end. I think that would be the best way to do that. So Themis is a professor of nanotechnology and also the director of the Centre for Electronics Frontiers at the University of Southampton, where he focuses on developing metal oxide resistive random access memory technologies and circuits for embedded applications. He also holds a Royal Academy of Engineering chair, which is the same chair position as Anna Cavalcanti also holds, because that's in emerging technologies. But Themis's chair focuses on developing novel power efficient AI hardware solutions and also a Royal Society Industry Fellowship. Now, it seems to me that because Themis likes to keep busy, he's also the director of the Lloyd's Register Foundation funded International Consortium of Nanotechnology, and that's how he and I first met. And that supports 50 or so PhD studentships, and he's also the co-director of the UKRI Centre for Doctoral Training, as well as founding a couple of companies in the last few years. So Themis, I don't really know how you have time to do anything, but I'm delighted that you found the time to join us. So if you're ready for us, then please do feel free to share your screen and we can get started.
So first of all, thanks for your invitation, Anna, I was hoping that the introduction will not be as thorough as what you sort of listed, but thank you so much. It's really a pleasure to sort of meet all of you, even through these unprecedented circumstances. Hopefully, when the time permits, I will be able to join you physically and visit you up in the north. So today I'll talk a bit about our work that we've been doing over the past couple of years on what I like to call AI on a chip. I mean, we heard this expression previously in terms of, putting labs on chips, putting, all sorts of different stuff on chip. But I think one important aspect in these era is how we can actually embed intelligence everywhere. And in order to do that, we need to identify what the challenges on hardware are. So hopefully you could see my screen. So I'll start first of all with a disclaimer that I'm an engineer, and as an engineer, I don't know so much about robotics, but I do like to spend a lot of time with my colleagues and my students in our clean room facilities. And this is basically what attracted me from Imperial, that I was previously in Berkeley in the States, to come at Southampton. We have £250 million in a clean room facility, which is unique worldwide, which really allows us to do some of the type of research that I will explain later on. So just a brief outline of my talk. I'll try to cover the modern electronics challenges and what the new AI era needs. probably I'm preaching to converted here, because you all are familiar with what I'll be saying most probably. But I'll introduce Memristive and the work that we do there. And I appreciate that probably have a rather diverse audience. So I'll try not to get into very technical details or too much on the material side of front, because there's a lot of interdisciplinary research that's happening there. And then I'll try to focus more on applications, some examples on applications, and conclude. So it's clear that our AI is as good as our access to data nowadays, and we've already exceeded what this graph shows, which is the plan was that we'll probably have about 50 billion interconnected devices, and I think we've reached somewhere in the order of 200 billion nowadays. The thing is, now these interconnected devices generated the loss of data, and this sort of data consumes so much power that it's predicted by 2025 we will be consuming at least a fifth of global electricity simply for handling the data. So we do need to do something, even if we were not to, just consider of any further progress in what AI means. So everyone's been very clear about this, that big data requires to be affiliated also and supported by a hardware revolution. And the key engineering challenge that I've been focusing my career on is how we can actually change the fact that so far we've been relying on electronics, where the fundamental design of memory and processing not being collocated places really a limit of what can be achieved. So how can we go from a classical von Neumann to a non-von Neumann sort of architecture? At the same time, as we start scaling devices further and further, it's really impressive nowadays to consider that the latest smartphones, they have about 15 billion interconnected devices, transistors, on which all this amazing intelligence runs. But in order to reach there, we've been making our switches, our transistors smaller and smaller, but we reached to a point where industry and the foundries, last year, Global Foundry mentioned that they will be stopping further investment into further scaling simply because it's not sustainable. So we're now hitting really the bottom, as Feynman would say, that there is plenty of room at the bottom, but actually we've really hitting the bottom now. So we need to do something about this. Memristive Technologies pose an interesting alternative beyond CMOS, beyond the conventional electronic technologies. And first of all, a couple of introductions. Memristive stands from short for the terminology memory resistor. And this was coined as a term from the chap on the left-hand side. I don't know if you can see my cursor moving. The guy on the left-hand side is Professor Leon Chua, who back in the 70s, a professor at UC Berkeley, with whom I've actually spent some time at Berkeley within his lab. He simply, from a symmetry point of argument, posed the question saying that there must be a component that he called memristor linking charge with flux, as for example, we have the resistor linking voltage and current. So entirely from a symmetry point of view, from the theory point of view, he posed the existence of this component, and he predicted how this component should actually behave, which is nothing more that when you stimulate it with a sinusoidal sort of a voltage wave, the current that you measure lags in terms of the maxima and minima, and then therefore you observe in the current voltage domain nothing more than this pinch hysteresis loop, which looks like an N8 shape. Now the guy on the right hand side is Stanley Williams, who a bit over 10 years ago, he was working on two terminal devices, metal insulator metal, based on titanium oxide for next generation of memory technologies. And his success was that he managed to experimentally demonstrate this behavior, but his big success was that he correlated that with the theory that Leon Chua predicted, over 40 years ago, in this very famous paper in Nature that they found the missing memristor. Now, this isn't new, and we have to be very careful here. And I've been quite vocal about this, writing commentaries in Nature, and there is always a little bit of reinventing the wheel sort of attitude in science. So we have to be very, very aware of all of that. In fact, I had a commentary in Nature Materials published a few years ago, where I've proven that Memristive is a subject that is almost two centuries old. Even back in the days of Faraday, they were experiencing this type of behavior. So why should we actually care? We care because these devices are highly, and when I say highly scalable, I'm showing you some of the examples produced in my labs here. So this that looks like a carpet here is an array of these crossbar devices, and they occupy about 1 by 1 micrometer. So within a 1 micrometer square, you actually have 1,024 devices. So just a couple of atoms wide. So it's highly scalable, but at the same time, they achieve more for less. And what I mean by that, so less space, as I've shown you already, but more memory states. So instead of having switches like transistors that allow you to store zeros and ones, we've demonstrated and we still hold the state of art in terms of analog memory capacity, where we've demonstrated even up to 7 bits over 100 distinct memory memory states. And these are non-volatile, which is quite exciting. What we mean by non-volatile is that you don't need to actually burn any energy to maintain that state. You just program it once and it stays there for as long as the material system can actually support it. In this case, you see like retention characteristics for over 8 hours. So imagine you have your computer, you save everything, you shut your screen, and then you open it up, and again, everything is powered up and is exactly where it was. And on the other side, it only consumes minimum energy. So this is picojoules of energy shown here on the bottom right-hand side. And you can see how you can access all these different individual memory steps. So essentially, it's like having a trimming element, like a tunable resistor that you can store a number of different memory resistive states. So enough of the, I hope this is clear for now. I felt that it's useful to put a little bit background on what memristors are and why should we actually care. So what can we do with this? So first of all, one example, which is of the obvious example, would be to use that to replace all non-volatile memory storage that we have in our PCs, etc. But today I'm going to talk about applications beyond memory, mainly showing how we can exploit this. For example, the first example is about performing in-silico machine learning implementations. So Eric Kandel in the 2000s, he got the Nobel Prize in physiology because he demonstrated that memory is transcribed in chemical synapses in biological systems. And if you look how a chemical synapse looks like, you look here on the right-hand side, again, abstractly as an engineer, what I see is there are these two terminals, so a pre and a postsynaptic neuronal terminal. And you have a barrier, which is nothing more than a synaptic cleft, in which neurotransmitters are diffused through the opening and closing of these ion channels. So when I see that as an engineer, that resembles to me a lot the following, which is nothing more than a cross-section from one of our actual prototypes, our memristors. So you have two terminals denoted in blue here, which is platinum, the top and the bottom electrode. You have a barrier in between, which is a titanium oxide layer, and you allow oxygen vacancies and titanium interstitials to move up and down in a rather similar fashion to biological chemical synapses. So we took that and we demonstrated for the first time a couple of years ago how these devices can actually be, first of all, perform as analog memory devices. You see that there is a certain operation regime that this can be utilized. So this is the voltage bias. You need to exceed a certain switching threshold in order to trigger a change in the resistance. And once you do that, you can run a number of different learning rules and learning protocols on these devices to potentiate, so increase the conductance or decrease the conductance of the devices. But the beauty here is that the change of the state is dependent on the history of the device. So what we show here is that, for example, if your device is at relatively low conductance and you're trying to push it in a higher conductance, so you're trying to learn something, the first time that you're learning something, it's quite easy to do so. And vice versa. If you're already up there and you're trying to do the opposite, it's easy. But if you're already in a relatively large conductance and you try to go even higher up, it's difficult. So we use that to encode conditional probabilities embedded within signals, and demonstrate for the first time with this simple winner-take-all network in-silico neural networks. I have to say that this was one of the very few to early career researchers here that who are listening us, that this was one of the very few times where we got some very useful and constructive feedback through the review process in Nature, where the reviewer said, this works really nicely, but how about if you were to implement it with probabilistic neurons? And therefore we did that, and we've seen that actually this topology works even better because it allows you to also to handle mistakes embedded in the signals, like quite well. So what you see here is the initial response of the system and the final response where the system becomes trained autonomously, and it's able to recognize the different patterns embedded in the system, in the signals. So bear in mind that because it's unsupervised learning, this is fantastic for implementation for embedded type of applications where the class senders drift over time. So you can actually let the system self-learn and then autonomously try to figure out how the classes senders move over time and start classifying that again. So that's just one example. A second example has to do with energy efficient Bayesian inference. And everyone is quite interested in nowadays in Bayesian inference and computing directly in the probability domain. It's something that's quite exciting for hardware. I don't want to really bother you with the details here on how exactly this was done, but essentially we're using as simple as that. We're using passive crossbar arrays of memristors and implementing simply Kirchhoff's law that allows us to add currents over rows and columns and allow us to do vector matrix, vector multiplication, by simply using passive arrays. Multiplication is one of the most expensive operations, if you like, if one is to implement this in hardware. So in terms of how many transistors you need to do that, how much power you need to burn in order to do that. So having such a simple and elegant approach to demonstrate that it's really fantastic. It's lowering quite a lot the constraints in terms of power consumption. And that's actually some work that we did collaboratively with some colleagues from ECS, from the computer science department that we presented at NIPS. So a third example is trying to look at new and alternative paradigms. And you probably heard it many times whenever someone is talking about a new technology, everyone is promising that, we will disrupt the paradigms, etc. But here we actually believe that we did something like that, and I'll explain how. So first of all, our world is analog. We don't see, smell, sense with a fixed bit precision. We are continuously processing analog signals. But nonetheless, for the power constraints that I mentioned previously and the scalability constraints of the technologies, our electronics is mainly operating in digital. So we have two very dissimilar worlds that need to be interfaced, and that's always posing a lot of challenges. How do you do the transformation between the different domains? And how can you become even more competitive? Now, the thing is that if we look at the different paradigms in circuits design, we have digital, we have analog, and we also have the so-called mixed signal, where the mixing of the two happens, but nonetheless, the mixing is happen at signal level only, as the paradigm says. If you look at the underpinning technologies, still this remains separable. And this is problematic because still we need to handle data and push data back and forth, which causes latencies and causes additional power consumption in databases. What we've done here is we try to effectively marriage the two these very two dissimilar words by the introduction of these analog memory devices, these memristors, with standard digital logic. So here is an example of a primitive component, an inverter, where you would expect to get this very typical transfer function characteristics for an inverter. But what happens if you start introducing these analog components in here? You actually skew the transfer characteristics of your inverter, and you end up having something that is allowing you to perform analog computation. And the beauty of this is that you can go and reconfigure, obviously, these memory states. So immediately by reconfiguring this, you can shape and you can tune these analog reconfigurable gates as you wish. And you might say, why would this be useful? Here is just yet another example that is using this concept. And with a very simple readout circuit, we're able to store different values here for creating in-silico classifiers that are very, very efficient, instead of relying, for example, to deep learning networks that indeed they are extremely efficient, but they consume a lot of resources, a lot of layers, a lot of time for training. Here we develop essentially very, very bespoke classifiers that are looking for very specific patterns. And this is extremely power efficient because it typically sits idle, consuming minimum power. And whenever you find the target, it raises a flag. It says, here it is, I got it. The beauty of this is that even when you are far off this sort of domain that you of interest, it tells you, this system tells you which way you need to move, which is really nice. And then why would that be useful? Again, classification and embedded classification is key into many different applications. Here we're just demonstrating that you can take this concept, scale it, and array it into what we call, it's a template matching pixel essentially. And you can scale it and you can array it and you can start looking at different biosignals. In this particular case, what you use it for in the end of the day doesn't really matter, because all of it is data in the end of the day, whether it's for natural language processing, whether it's for for image processing, you can still utilize that. And the only thing that it would actually change is the number of pixels that you can actually tessellate in an array. So moving on, here is yet another example that employs the device physics, but for sensory data compression. So everyone is talking nowadays how important it is to devolve some of the computation that happens in the cloud to the edge. What do we mean to the edge, right? Because again, that has many different connotations, many different meanings. Perhaps in the robotics community, it could mean within, like the framework of a robot and the onboard computer running that. For the smartphone community, of course, it means the smartphone, the handheld device. Here specifically, we're talking at device level, so at the individual memristor. So allow me to explain a little bit more for that. So if you look at a standard memory device, like the ones that we prototype, if you start stimulating it with voltage pulses, nothing happens until you exceed the switching threshold. So ideally, you have these two thresholds, which is a soft breakdown and a hard breakdown. Above this, the red area, we don't want to be, because we're causing irreversible damage into our oxides and our devices. But this is where the magic happens, the reversible switching. So below that, nothing happens. There is no change in the conductance of the device, as also shown here with this sort of data. So as you start going over these thresholds, you start registering these non-volatile changes in resistance. Now, if you take this, as I show you here, essentially this demonstrates that the device has the intrinsic characteristics of a threshold voltage integrator, that we can actually utilize it, and integration is fantastic always for sensing, and that's exactly what we did. Here are just some examples with colleagues from the Max Planck Institute, where we were getting biosignals from rat neurons, sensing those with a multi-transistor array, and then just converting those into appropriate sort of pre-amplifying the signals so that we can induce changes in conductance. Now, what is very interesting here is the information is always inhibited conveyed, if you like, in the spiking events here of these biosignals. Now, there are two things that people in the electrophysiology community are interested in, is whether there is an activity, so whether there is a spiking event, which is known as spike detection, but also to which neuron that spiking activity belongs to, which is essentially spike sorting, right? So in this particular case, we know nothing about the number of events that exist. And when we bias these devices with this type of signals, you see changes in the resistive states that are, done in a passive kind of way. If you take this input and you invert it, you could see that there is an analogous change in the other side, resistance and so forth. So that's just a sanity check. But through that, we can actually count events. And this is shown much nicer here, where you see 3 different types of events, and you see each one of them registering a corresponding change in resistance. Now, this is important because in other ways, we would actually need to spend a lot of power. In this particular case, we demonstrated at least 2 to 3 orders of magnitude reduction in terms of power consumption per channel from the state-of-art system that does spike detection. And this is happening because simply we do not have to be continuously on. The devices, we do not need to oversample, like our multi-transistor arrays, so that we can make sure that we monitor every single event. And the devices passively accumulate this information. But the other beauty of this is that not only they do that, but they, depending on the envelope of the signal, they change their resistance in a corresponding way. And because they do that without really bothering you too much in the details, you're also able not just to perform spike detection, but also spike sorting. Because if you were to plot it in this particular way, where you're looking at the fractional changes of resistance per event, you will see these lots appearing naturally. So instead of doing template matching externally, which causes a lot of constraints in terms of the bandwidth and in terms of power consumption, you probably need a supercomputer to do that at large scale. You can actually do that, delegate that really at the edge, at the device level. Now, why is this important? Allow me to say just a final point on this example, because bear in mind that most neuromorphic type of sensors nowadays, whether it's smart imagers or microphones, etc., they operate with spiking events. So although this was originally developed for biosignal analysis and for electrophysiology, a tool for electrophysiology, this is actually fantastically applicable to so many different other areas that spiking events are utilized in the communication. And the final example I believe I have here is, once you have a device and a technology that speaks the same language with biology, immediately you have a great technology to act as the link between biology and engineering. And this is a piece of work that we completed sometime last year. It's part of a multi-parties project, European project, and done collaboratively with the ETH and the Institute of Neuroinformatics, the group of Giacomo Indiveri and Stefano Vasanelli from Padova. What we've done is we've demonstrated for the very first time that we can link through these devices, Memristive devices sitting at Southampton, we can link the functioning of real neurons to artificial neurons. So essentially, we've demonstrated for the very, very first time the link between real and artificial intelligence, and backwards as well. So we recorded the activity of real neurons cultured on multi-transistor arrays. The signals were sent over UDP. By the way, this is an example that has attracted a lot of attention, not only because it's, personally, I'm quite excited because it's really cool. It's the first time that real and artificial intelligence is merged bidirectionally in real time, but it was also done over the web. And it was actually an example that we did, which helped us really a lot to continue with our research during this COVID lockdown. because we were simply doing that from instruments that we've developed through one of my startup companies, as Anna mentioned, ARC Instruments, that allowed us as well as collaborators to run this from our bedrooms, essentially. So this was really obviously not the neurons, right? There are certain ethical constraints there, but it was really great fun because we can do that over the web, and we can in fact demonstrate a geographically distributed biohybrid neural network for the very, very first time. It's scary, but it's extremely powerful. This was done for very, very few channels, and we're now working on, which is reported in this paper in scientific reports, but we're now working on much larger scale sort of implementations to do real-time interfacing. So really, what's next? I mean, Anna mentioned my Royal Academy of Engineering chair in emerging technologies, and I've spent the past decade or so from my career focusing on developing the technology, maturing the technology, and the infrastructure and the tools that we need to have for using the technology. And now going forward, you know, we're focusing more, especially under my Royal Academy of Engineering chair, in particular large-scale implementations for AI chips. So we've identified 4 key computational pillars. I've already explained a few of them: the sensing front, recognition with in-silico classification. How do we exploit these sort of new emerging technologies for continuously on systems that they have more and more needs in terms of memory storage? And if you, for example, think of biological systems, you know, it's not, we still are constrained from a finite number of resources, right? But we don't just do what, you know, like a hard disk will do. Whenever you reach its maximum capacity, let's say 1 terabyte capacity, you can't store anything else. This is known as the palimpsest problem, which is quite an exciting computational problem, where we keep learning new things on top of old memories, and we maintain both. But the compromise is how easy it is to recover old stuff, right? So that's we have already some preliminary work in that area, which is very exciting. And of course, reasoning. You know, if I was to ask you, what is the $ of the UK? Immediately you would come up with an answer. You know, you will think that he is probably talking about the pound, right? What $sign? A pound, a pound. But if you were to ask a computer the same question, you will not get any response, simply because there are 2 data sets that are completely uncorrelated. Nonetheless, there are correlations there. So manipulating symbols and symbolic processing is something that we're quite excited with, which is obviously very exciting for robotics as well. And having hardware to do that, it's truly exciting. And because I like to dream, is the way I see that is that if you have these 4 core capabilities, which in my opinion define machine intelligence essentially depends on the ability of a machine to sense its environment, recognize some patterns, learn something out of that, and reason. So you can you know, sort of pave the way towards thinking machines effectively. I've got a little video.
Artificial intelligence is transforming the way we interact.
Does it sound okay?
Artificial intelligence is transforming the way we interact with the world. It allows us to automate routine tasks and even augment our abilities. Over time, the use of AI broadens, but so does the amount of data generated, driving current infrastructure to its limits, demanding ever more data bandwidth and energy. We address this problem at its source, embedding intelligence everywhere by delivering AI on chips. Our solutions are powered by a new electronics fabric that we have developed over a decade of research, which uses nanotechnology to achieve computation, memory, and energy performance impossible to deliver by modern electronics. To support the creation of intelligent machines, our AI chips enable 4 core capabilities: intelligent sensing, pattern recognition, online learning, and reasoning. Our sensing chips address the power and bandwidth challenges of big data by compressing information on site, allowing monitoring more sources in parallel. Our pattern recognition chips empower local classification capabilities, minimizing the need to share sensitive data online. By being less dependent on cloud computing, these emerging AI systems are able to react faster, allowing to make critical decisions in real time. Modern electronic systems are progressively operating continuously and often need to memorize events quickly and over longer periods. Our advanced learning solutions can support such emerging needs without saturating memory resources. Our solutions are designed in ways that they can empower machines to reason and apply logic and common sense like humans do, enabling them to use judgment when dealing with new situations. These core capabilities pave the way towards intelligent machines that are destined to revolutionize the use of AI in serving modern society, enabling smart assistants, autonomous vehicles, and neuroprosthetic devices. All made possible by our vision for embedding intelligence everywhere.
So that's essentially, in a nutshell, the vision for the work that we're doing within my Royal Academy of Engineering chair. We already started developing some of these activities. Of course, COVID caught with us, and but things are going quite well, I would say. So I mean, just in a nutshell, how could possibly the future look like? I think a key and exciting prospect is that the privacy of the data, the fact that you're able to change the where the computation happens, and that business model provides some other exciting opportunities. And by having not having to share your data continuously with the cloud, you're enabling other alternative unprecedented opportunities for the users. Maintaining the privacy is just one example, right? I think in the video was also mentioned the real-time responses and minimizing latencies, which could be also particularly important for autonomous vehicles, as well as robotics. The other thing that we're working on as part of my Royal Society Industry Fellowship is collaboration with Galvani Bioelectronics, which is spun out from jointly from GSK and Google about 3-4 years ago, with $500 million into that. And really the vision is that the next generation of medical interventions would rely on electronic devices that will be monitored in real time our biosignals and intervening in situ, rather than using drug compounds that also have side effects. You can immediately see Anna et al, like all the security implications and the ethical implications, and I'm very happy to discuss on that as well. And of course, because I said I'm a dreamer, I like to think that the work that we demonstrated recently really paved a very, very small step towards the interaction of artificial intelligence and real intelligence. What happens, I mean, if, for example, can you displace dysfunctional parts of the human brain with neuromorphic chips running in these technologies? For example, people suffering from Alzheimer's, or can you get an upgrade yourself? I certainly might need one in a few years' time, or maybe even now. So as Feynman said, and I'm very fond of Feynman, what I cannot create, I do not understand. And I think there are really great opportunities to also utilize these technologies for modeling biological systems. Of course, there is a lot still that we need to do, and we've been quite vocal about this. And this is just one recent commentary we published in Nature Comms, where we described, what are the challenges hindering such neuromorphic hardware technologies from going mainstream. The technologies are still at their infancy. So you can imagine there is loads of issues with yield, with reproducibility, with availability of these technologies across different groups, but we're getting there. I mean, Intel has already recently introduced products that depend on this type of technology. So what's the space? And we're trying to do as much as possible on our side. So this is a service that we are trying to establish across the UK, which was provided through a program grant that I'm leading called Forte, which is collaborative work between Southampton, Imperial, and Manchester, where we develop the technologies and we do that, the monolithic integration of these technologies together with CMOS circuits. Southampton is uniquely located to do that because of the large scale prototyping facilities that we have available. So now we're putting a recommendation there to provide this as a service to the broader electronics community in the UK. And there is a lot of excitement there, because that can possibly give us an edge, if you like, in terms of the next generation of AI system. Of course, what I've described is not my work. It's thanks to all of these fantastic people, and of course the funding that we had from a variety of sources, mainly RC UK, as well as Royal Academy of Engineering and different foundations. So with that, I think I'll stop here, and hopefully we still have time for question. I hope we very much didn't lose everyone in the material sort of side of things or the technicalities, but I'll really be glad to get any questions.
Themis, thank you very much. That's fascinating, and it's I'm glad you're not looking to upgrade your own brain, because then you will be unstoppable, I think. But it's nice to see that your group has thrived even in 2020. So really, I'd like to open the floor to our colleagues to ask some questions. Perhaps you could unshare your screen, and then we could have people on a gallery view, which would help everyone to see each other. Does anyone have any questions? You're all currently muted, so you'll need to unmute yourselves. And I can't see everyone waving, so please do speak up.
Has a question. Colin Patterson has a question on it.
Hi there, thank you. It's really interesting and exciting stuff. I'm sorry if this is a naive question or I misunderstood. You have some really interesting characteristics of your electronics there, that we end up going from binary to nonlinear analog features. I guess my question is, how does that change the stack that we need to have in terms of developing these things? And even things like, obviously, my experience in neural networks, we understand the nonlinear characteristics and we can do the learning with respect to them. What do we have to do here? Does this change everything completely in the way we work with these electronics?
It does. This is a really exciting question, but very challenging, obviously. So software needs to be co-developed, first of all, right? And also the way that we design our electronics, it needs to be, I kind of feel like we are, I don't know, 70 years back, when transistors and integrated circuits were introduced by Kilby, and we're trying to figure out how we can actually do logic, right? So there are the concept I've shared with you, which was published in Nature Comms. The only reason it made it into the Nature group was because it was completely changing the perspective, and it was as simple as saying, okay, we have an integrator, a digital logic gate. What happens if we start introducing like these analog components in here, right? Which was as simple as that, but it led into so many different areas. And if you look at the paper there, you will see there is a place start to unpick one by one of the opportunities that we have there. So you're absolutely right. We're still in the infancy of the technologies. We're still developing all of that. And actually part of my program, Grant, is exactly looking at providing and developing the technology as well as the infrastructure that goes with it. So for example, models. We work with cadence systems so that we can develop new design rules and new PDKs for people to design with, right? So it's not easy. There is a hell of work that needs to be done. But I think the opportunities are really, really exciting. And from the computational point of view, there are some unprecedented opportunities. Memory computing allow you to highly parallelize processes, computation and storage in one location.
Thank you.
I hope that answers.
Yes, thank you very much.
That we're still trying to figure out, what's the best way.
So I think we've got a slight lag with the video. I'm certainly.
Any other questions?
I'm certainly hearing a little bit of breakup, but thanks, Themis, for that one. Anyone got any other questions? Then just either let me know in the chat that you have a question, and that's probably the easiest, so I can spot you, or speak up.
Stephen Wright has a question, and he raised his actual hand.
Thank you.
Sorry, yeah, I was. You mentioned the irreversible switching stage and a reversible switching stage in the behavior of the device. I just wondered if there was a life issue on the reversible, because the device is history dependent. Is it something where the characteristics change over time so that the device has a finite life?
Yes, so there's a couple of points there. So all electronic components have a finite lifetime, right? I mean, the same is true for standard flash, NAND memory. Okay, and the same is true for Memristive Technologies. The reason I've made it explicit about this irreversible regime of switching is because we get a lot of reports in the literature of people showing this eight kind of figure, this pinch hysteresis loop, which is not actually something that's repeatable and reproducible, but it was the source of a failure of a device that has actually broke down, and they've observed it once and that's it. So failure is resources are the more the resources are utilized within a device, the shorter the lifetime of that device. Okay, and likewise, maybe I use it as an example. Someone told me once, live fast, die young, kind of, right? So the same is true here for this type of devices. If you start using them at, with large on-off ratios at the extremes and switch them on and off all the time, you would expect that the lifetime will be significantly reduced.
Okay, thank you. Does it drift before it fails, or is it a hard failure?
It depends how you reach to that point. So it's not a straightforward response there. However, we have some recent work that we've done, one of my PhD students, where they've shown that you can actually recover devices by exposing them into higher humidities. You can actually, the devices can be reoxidized internally, and you can bring them back from death, which is very interesting.
Okay, thank you.
Any more questions, please?
I have a question before this don't. Themis, if I could please ask an unfair question. I think I'm sure you're aware that people have been very concerned about the use of AI and the possibility of assuring and verifying these systems that are involved in learning as they go along. And there's been quite a lot of work on the use of mathematical techniques for verification of learning applications. And of course, these mathematical techniques have in the past been extremely successful in the area of hardware design. So I wonder if you would know about works in this particular area where people are taking the approach for mathematical verification of applications in this area. I realize it's an emerging technology, and perhaps there hasn't been no time for that kind of thing to develop, but just wondering.
No, actually there is quite a lot of work happening in that front as well. So just as an example, yesterday evening we had our, similar to your seminar, the CEF invited seminar, and we had someone, a senior developer from Synopsys from California joining in to give a talk, and he was talking about logic synthesis and verification, and as you could expect, the discussion revolved in the end around what do we do about these emerging technologies as well, and they are on the case. They are on the case because there's a lot of once you have Intel and the likes of Intel getting involved in producing products, that naturally happens. I have to say it wasn't difficult for us to convince Cadence and a number of other big companies to be involved in this research and the research that we do in our program grant. In fact, we started with something like 5 or 6 industrial collaborators, and probably we've tripled. Over the, so yes, definitely, it's something that is very important. The problem the community has at the moment is there is no particular flavor of technologies. Bear in mind, there are loads of different materials that do the same stuff or similar kind of switching. So until someone like TSMC, one of the key foundries, comes on board and they say, they already do that, by the way, and they say, this is a technology that we've developed, and this is now becoming mainstream, and we provided, a commercially available technology. That would, in Italy, it would allow everyone else, when they do verification, logic synthesis, etc., to follow. Because at the moment it's a little bit segregated. Okay, we got a program grant to do that within the remit of the program grant, but I think that's the best that you can actually do. If I may respond also, someone said in the previous comment about how it was discovered by students. Did someone spill water on one? Kind of, right? So we've always struggling in finding, like working devices in the group, right? So one of my PhD students that was part, he was still at Imperial when I left. I was providing him with devices, and he was burning these devices, like, I don't know, 1 package per week or so. And these are quite expensive at prototype stage. And at some point, he had a stack with all of his samples. And because he ran out of devices, he went back and he started characterizing some of the old devices, which were all presumably dead, but they would be sitting on his desk for months, if not years. And he realized that the majority of them were actually all working. So this is kind of what triggered the further experiments we did, and we had a student who triggered it, like by introducing these devices intentionally after they got into this irreversible sort of regime, into high humidity type of environment to recover their operation. So yes, kind of by accident. A lot of stuff happened by accident. And my suggestion again to students and early career researchers is don't be afraid to make mistakes and break things. As long as you don't break something super expensive, like at the equipment and all of that, but the rest, consumables, is to be, broken down and to use them. Otherwise, you won't be able to discover anything.
And perhaps never throw anything away. That could be your other advice, even if it's broken.
Yes, indeed.
So we have a question from Danish about about machine learning in applications. Danish.
Thank you. So just following from what Professor Cavalcanti said, I come from a background in advertising and data analytics. So excuse my ignorance if it's probably an answered question in the industry, something I don't know. But without trying to sound too George Orwell about this, how is the direction of this technology managed or regulated? Because if we're relying on machine learning to essentially mark its own homework, how do we as humans or engineers intervene to keep the learning in check? Because from my previous experience, what we designed as product designers for example, I worked in social engineering and advertising, we allowed the machine learning to assess itself and essentially upgrade itself. And what happened was what we planned compared to what the end result was completely different. So how do we manage this when AI or machine learning is capable of modifying and upgrading itself to such an extent?
That's a brilliant question. In fact, the challenge here is even worse, which we actually utilize as a benefit. And let me elaborate a little bit more on that. You probably have seen in the news how particularly Chinese firms that try to sort of reverse engineer designs of prototypes, and they have these very, very elaborate techniques where they start sort of removing layer by layer from ASICs, from chips, and through understanding what the architecture of the chip is, you can understand what the functionality of that system is. Here is almost impossible to do that. So Memristive Technologies are actually quite nice for embedding security in a way, because the actual operation is programmed within the device stack. in the way that the atoms within the device and interstitials are oriented. So there is no way to reverse engineer that from that point of view. All right, so that's why I meant that it has a different connotation as well. Now, in terms of the verification and from AI's point of view, this is exactly why we went down the route of symbolic processing, because I mean, it's important, especially for assurance purposes, to see where things go wrong. Okay, and again, I'll give an example. If I was to ask my 10 years old sons, you know, like what they did wrong at school, if I was to use that exact language, they would spin it around and say something that, you know, no, we didn't do anything wrong, it was someone else's fault, etc., etc. So I need to develop my own language in order to interrogate them and get to the right question that I'm after. So I think the whole framework of symbolic processing, and instead and using that for a more transparent, if you like, AI operation in the system level, it's in my opinion an extremely powerful tool. And we did a project with DSTL and Thales in that particular domain, which kind of triggered a lot of other actions there. So I think that's probably the best way one can go about, rather than looking at what was the individual memory states per device, etc., etc. Even with conventional electronic technologies, you won't be able to do that, as you rightfully say.
Thanks, Themis. So we've got time for just one more question that's coming from Matt Dale. Matt, do you want to ask this one live?
Yeah, sure. I just wanted to ask, so variability is a big issue with memristors. Do you know anyone who's actually trying to use this? Because in many ways, I mean, a lot of work is about building a universal component that we can use to make cognitive systems, whereas it might not actually be universal components, that they will have variability in them. Is anyone actually trying to exploit this?
Again, that's a very, very nice question. So just for everyone's interest, you know, you fabricate 1 million devices, and then each device will sort of diverge from its operating regime, you know, like you will have, which is typical for also commercially available electronics, right? Especially as you do more scaled versions of them. The same is true with memristors, and even more, right? Because we're leveraging these highly rich dynamics based on these metal oxides redox operations. There are two ways of thinking here. There is the one which says, where my program grant comes in and says, we would like to have as much as possible repeatable, you know, operation from device to device and cycle to cycle repeatability. And what we try to do there, of course, is improve the yield, improve the repeatability of our processes, but also develop mechanisms and tools that account for this type of variability. So the models, we build now statistical models that take into account thousands of measurements and provide you an operating regime to give you some confidence when you design an application. At the same time, and I don't know whether you were reviewing a recent proposal of ours. There was this call for proposals recently on AI efficient hardware for computing, where almost everyone I know from the neuromorphic computing in the UK was involved with, and we had a collaborative program that we submitted there with Imperial, where we said exactly the opposite. We said, let's accept whatever the variability is, and let's take that as a feature and use AI to sort that out. Sadly, the panel still hasn't happened, but sadly the reviewers couldn't really see what exactly was it that we were saying there, but who knows. The best of my knowledge, there aren't really many people at the moment talking about this aspect. I think there were some people with commercially available CMOS technologies, because it said similar issues exist there, but not in Memristive Technologies, as far as I know.
Great, thanks.
Thank you very much, Themis, and thanks to our audience for some interesting questions. It looks like you've got everybody thinking about what they can be doing and what other things they can be not breaking. It's been really nice to have you here with us, and it's been a really great way to kick off the YorRobots series of seminars for this academic year. So thank you very much for being our first speaker for this year. There will be more, and so anyone who's on our mailing list for the YorRobots will be getting emails about that. I can't promise they'll all be as fascinating as Themis, but we'll certainly try. Thanks again for all of you for attending, and see you again soon.
Thank you both. Thank you, Themis. Thank you very much.
And
Thank you.